Hello everyone. Today we are going to start with a very important concept in this course, which is called complex differentiation. So what exactly is the differentiation that you already know, right? So in real terms, what happens is, let's just recall it like this. Let's say f is from open AB to R, right? And you say is differentiable at the point x naught if, what do we say, from the first principle, limit s tends to 0, f of x plus h minus f of x by h, this limit should exist, and if it exists, okay, then we call that as then the exist, and we say f prime x is nothing but this limit. Okay, so we say this is f is differentiable at the point x naught. That is what we define. Okay, so this is our definition from R to R, AB to R, or R to R, right? Now you see this definition depends on few factors. If you recall, look at this particular thing. This is just a motivation of it, right? See, we are taking this particular value f of x plus h, and we are taking this value f of x, right? So you are taking two values, or taking 2 points, x plus h and x, and we are looking at the difference between the value of f at those 2 points, and then we are dividing it out by h. Is it okay? And that h, this h tends to 0, this h is a real number. Okay, so and then we are taking the limit as h tends to 0. Okay, now here what is happening is this. See, this is where the difference of, as I told you, between R2 and C, as I said, these two particular R2 and C are kind of same, right? They look, the type of element are exactly like same. But the problem is, why we are studying this particular analysis is because the underlying structures are different. In R2 addition, x is in R2, y is in R2. It means x plus y is in R2, right? We know that. Now, let's look at a C. In C also, x and y, let's say these two elements are complex numbers. X is a complex number, y is a complex number, and you can add it up, right? X plus y is also a complex number. So basically, you see, the addition part of it is essentially the same. So whatever, okay, see addition, up till addition, the set has exactly similar looking elements, right? If you identify a b with a plus ib, then actually they have similar looking elements, and addition is the this operation is exactly the similar sort of operation. So if you are defining some concept using addition, so the concepts which we defined using addition, those concepts, addition, absolutely no issues. They actually are same. Whatever it is there in R2, they are same as in C. So for example, you have looked at the definition of continuity, or let's say the definition of limit also, same sort of thing. Yes, but here in differentiation, you see, it depends on how we are defining the particular definition. So if we look at this particular definition of R and we want to write similar sort of definition in C, because we can identify some part of C which is x0, this part with R, right? With R. So with x which is in R. So you see, for elements of C which looks like x0, for those elements, the derivative, the idea of derivative at that point should exactly work like R, right? So we can actually, motivate ourselves for the definition which goes like this. So what is the definition? So the definition, okay. So let us assume f is from C to C. Yes, I am writing it C to C, but you can write it as omega subset of C, which is open, to C. Yeah, we can do that, but let's just assume here like this. F from C to C is said to be differentiable, to be differentiable at Z naught in C. Yeah, a complex number in C. If you are defining from here omega, which is an open set in C, then it will be in omega. Okay. Okay, so I'm not writing that part. I'm just, assuming that here it is whole of C. So we can just move on doing that. Okay. So at C, if limit h tends to 0, exactly similar sort of thing, limit h tends to 0, f of x, z naught plus h minus f of z naught by h exists. Okay, and in that case we call it a prime of z naught, which is essentially this limit. Okay, so again, see here, all of this makes sense. Why it makes sense? Because f of z naught plus h is a complex number, for each h, for all h, yeah, in C. Okay, now f of z naught is also a complex number, okay. Now if we take the difference of those things, f of z naught minus f of z, that is defined, right? That is a complex number again. And incidentally here, if we divide this particular thing, you see f of z naught minus plus f of z naught plus h. Okay, and if we divide this particular complex number with h, which is also a complex number, that particular thing, until so assuming h is not 0, that particular this particular quantity is well defined. Yeah, because you can divide complex numbers. Yeah, so see, this is the difference between R2 and C. In R2, things are vectors, right? So let's just assume here, if we just replace this similar sort of definition with R2, let's say R2 to R2, let's just assume, see what is happening. As similar definition, what it gives is f of let's say z naught plus h minus f of z naught by h. If we write it, in this case h will be in R2. In this case h is in R2. It's a vector. Now you see this particular quantity. This is a problem. This quantity is not defined in R2 because you can't divide with a vector. Yeah, this is not defined. So that is the whole issue. In R2 you can't define the concept of derivative like this, but in complex you can, and that is what actually differentiates the whole analysis of complex with that of a vector calculus. Okay. So I hope this is very clear to you. And with this definition cleared, we can of course look at some examples. So let's say what sort of functions we already know. We already know functions which looks like a polynomial. Let's say f of z is z square. This is a very nice function. It should be a very nice function, right? Okay. So in this particular thing, let's say that this is a function f is from C to C. No questions about it, C to C, right? Okay. So how do we look at this thing? See, we can look at it. So I want to talk about the derivative of it. So let's say f of z plus h minus f of z by h. We want to look at this particular thing. So that is nothing but z plus h square minus z square by h. Okay, and then we take limit h tends to 0. Limit h tends to 0. Okay, if we do that, now this is nothing but limit h tends to 0, z square plus 2zh plus h square, okay, minus z square by, okay. Now you see we can subtract these two particular thing, and limit h tends to 0, this becomes limit h tends to 0, this becomes 2zh plus h, so 2z plus h, 2z plus h, okay. And then if you write it down, limit h tends to 0, 2z is nothing but 2z, and limit h tends to 0, z is nothing but 0, h is nothing but 0, right? So it becomes 2z, which is our usual thing. We already know this is going to happen. Yeah, remember, see, f of z equals to z square is essentially, think of it like in R2R, f of x equals to x square, and you know what is the derivative, which is basically 2 of x. Yeah. Okay, so this is very, very, expected. Huh? Let's just look at another example. Okay, B. Now, let me just ask you, let's say fz equals to, so a question, question. Let's say fz equals to z power n. Huh? What is the derivative? Find the derivative. So essentially, first question is this: is it differentiable, and what is the derivative? Huh? You can of course guess what is going to happen. So please look it up, but do it properly. Okay. B. The another question example. Let's say fz equals to mod z square. Now you see two different ideas. See, in the first thing, it is a function f is from C to C. Clearly C to C. Huh? Of course, the second part we'll look at it, but in this case, f of z equals to z square is C to C function. Okay. In this case, f of z equals to z square, mod z square, is from C to essentially R. Huh? But you can of course treat it as a function from C to C, because R is again a part of C. You can treat this function, and it's a very, very valid function. Absolutely no issues here. Let's just look at if we can actually, if we treat it like this. So here the function f, you can think of it like f is from C to R, right? C to R. Okay. Now the question is this: can we talk about whether this function is differentiable or not? Okay. What do you think now? What happens now? See, this function f. Let's look at it. Limit h tends to 0, f of z plus h minus f of z by h, which is limit z tends to 0, mod z plus h square minus z square by h. Okay, this is nothing but limit h tends to 0, z plus h bar minus z bar by h. Remember, right? See, mod z square is nothing but z bar. Yeah, this we already know. Yeah, so we are using that particular formula. Yeah. Okay, what are we here? So this is nothing but limit h tends to 0. Let's just break it up. Z bar plus z h bar plus z bar h plus h bar minus z bar by h. Yes, that is nothing but limit h tends to 0. Now you see, we can cancel these two part up, and then we left out with this z h bar by h plus z bar plus h. This is what we have. Now that is nothing but limit h tends to 0, if it exists, of course. Z times h bar by h. Z is independent of h, so we can push it outside, plus limit h tends to 0, z bar plus limit h tends to 0, h. Clear? See, this is going to 0, no issues. Yeah, this is nothing but z bar. What about this thing? Let's just look at it. See, the first limit. Okay, see, this is a issue here. So we have to find the limit of h tends to 0, h bar by h. Yeah, and remember what h is a complex number. Clear? Okay, so what happens now if we want to find it out? See, this limit does not exist. Does not exist. Yeah, this we already know. Why? Because if we break it up, let's say h is nothing but h1 plus I h2. Let's just assume this is a complex number. Let's just break it up. That will imply that h bar is nothing but h1 minus I h2. Now, you see, if we take this kind of thing, so limit h tends to 0 means, and limit h tends to 0, this implies this implies that both h1 and h2 in real sense that also goes to 0, right? So you see, if we take two different paths, so taking, you see, let's say h2 is 0, take this path, take h2 0. Yeah. So as I told you, in this kind of thing, limit, the idea of limit, I mean, if it has to exist, it has to exist in every particular direction. Yeah. So limit h tends to 0. So basically, let's say h2 equals to 0. I am taking the path h2 equals to 0 and I am pushing h1 towards 0. Yes. So in that path, what happens is, therefore, this particular limit h tends to 0, h bar by h, that limit is always going to be 1. Yeah. Because you see, h bar is nothing but h1 minus I h2. So h2 is 0. So it's basically h1 by h1 and limit h tends to 0, which is h1 goes to 0. Yeah? h1 and h2. So basically limit h tends to 0, limit h tends to 0. Is if limit h tends to 0, it means that h1 and h2 both are going towards 0, right? So you see, this is nothing but 1. So that is why it is 1. Okay. Let's just look at a different idea path. So we take h1 equals to 0, and h2 is going towards 0. Then what happens is limit h tends to 0, okay, h bar by h, that is nothing but limit h2 tends to 0 minus h2 by h2 here, which is minus 1. Now you see, two different paths, two different limits. So this limit does not exist. Yeah. So therefore, the limit does not exist. Does not exist. Clear? So once it does not exist, hence fz equals to mod z square is not differentiable. Okay. Now, one question, I want to pose a question here. Question: is fz equals to mod z square differentiable at 0? Yeah. So essentially what I am asking is this. Of course, if h is not 0, so here you see, if z is non-zero, yeah, this is always true. That's not the point. Yeah. My question is this: if, let's say, see here, if you just look at it, see this particular term is there. Yeah, that is there because z is not 0. If z is 0, then this limit actually, you don't have to go to this limit. You see, it becomes 0 far here itself. You see, here this term does not exist. This term does not exist. Okay. So essentially in that case, it is h bar by h, which is h bar, and limit h tends to 0, h bar is going to be 0, right? So in that case, the limit does exist. Okay. So the question is this: see if it is differentiable at the point 0. It is actually, yeah. So you can actually do that. Now, the very important question: is there any other way that you can actually find that the limit exists and any function is differentiable and that sort of question? So essentially, the question is this: is there any way we can prove that a function is differentiable other than calculating this whole particular first derivative example? Okay, so this takes us to something called Cauchy-Riemann. Okay. Another question. Yeah. Sorry. Yeah. Let me give you another example. That will be a very important example. Let's say fz equals to z bar. Yeah. So these are the only few examples which we know. Yeah. Of functions. So, z square, z bar, mod z square, this sort of thing. Fz equals to z square. So this you can actually show that this is also not differentiable, not differentiable. Okay, not differentiable. Yeah, and this is quite easy. Exactly the similar sort of I mean analysis which you did, you can actually do it and to show it is not differentiable. Yeah. So this is another question. I'm just putting it as a question. Okay, right. So now let's look at the alternative thing. So this is called the Cauchy-Riemann equation. Cauchy-Riemann equation. Okay, this is one of the most important topics in complex analysis, Cauchy-Riemann equation. Huh? Okay, so what is it? So let's say that if you have a function f is from C to C, huh? The question is about derivative, if derivative exists and or not. Huh? So it's basically you can think of it as a test for derivative. Huh? So we want to test whether a function is differentiable or not. That sort of test is this particular thing. Huh? So you are given, so let's say given f is from C to C, huh? And say you see f of z, huh? So and let's assume, okay, I'll put it this way, and let z is in C, z and w is in C, huh? Two numbers, z and w is in C. Then we can write it like this, right? W is nothing but f of z, right? See, f of z is a complex number. Let's just write it as w. And then what happens is you can break it up, right? So you can break it up into real and complex part. Real part is u of x comma y plus I of v of x comma y. This is always true. Yes. See, z here, z is x plus iy. Think of it like this, x plus iy. Okay, right. We have already looked at it, right? That any complex number f from C to C can be written as a real part and an imaginary part. Yes. Okay. Now, see, basically what we want to do is we want to see whether this sort of function f is from C to C given by this, yeah, is differentiable or not. Yes. Okay. So the theorem says, this is a theorem, and it is a very, very important theorem. Huh? Please keep this in mind. Very important theorem. This is called Cauchy-Riemann equation. Let's say let f of z is u of xy plus I v of xy. Okay, I v of xy, and be defined and continuous. Okay, in some neighborhood. I am writing it like this: neighborhood. Huh? You have a neighborhood of a point z, which is x plus iy. Clear? Okay, and is differentiable. So you see, with the idea, the knowledge of what derivative is, we are using that knowledge here. We are saying that this particular function is differentiable in some neighborhood. Okay, in some neighborhood of what? In some neighborhood of a point z, which is x plus iy. Then at that point, so basically which point? Z. Okay, at that point, the first derivative, the first order partial derivative. Okay, see here, f of z is decomposed into as u of xy plus I v of xy. Huh? And what is u and what is v? U is a function from R2 to R2 to R. If you look at it, it is basically this. And what is v? V is also a function from R2 to R, right? Because x and y, you can treat it as R, which is R2, and then v is also x and y, which is R2. And the value u of xy is R plus I R, which actually gives you C. Okay. So essentially, that is why, since u and v are two particular functions, which is R2 to R, real valued functions, then the first order partial derivative of those functions exists, okay, of u and v exists. So basically, if the function is differentiable, then the first order partial derivatives exist and satisfy the CR equation, satisfies the following. So this is the following particular thing is called CR equation. What is it? It says that ux equals to vy and vx equals to minus uy. So these are called CR equation, these two particular things. Okay. So again, what we are trying to say is this thing. Here, the function initially, the main function which we have in hand is a function from C to C. Yes. But now what we are doing is we are not really interested in C to C. We are breaking the function up into two parts. So the two real function, you understand? See, okay. The motivation is this. F is from C to C. Yeah. But we are breaking this F into u plus iv. Yeah. Where u is a function from R2 to R, u and v, where u and v are functions from R2 to R. Real functions, it's a real valued function, okay, which is defined in R2. For such functions, we are much more comfortable with such functions. We already know how to deal with this. So what we are saying is this: if the original function is differentiable in complex differentiable, basically, yes, if it is continuous and it is differentiable, then what happens is this: then the first order derivative of those two real from R2 to R function, the real part and the complex part, those part, the first order derivative exists and they satisfy the CR equation. What is it? It is basically ux equals to vy. So basically the first derivative of x, ux, is nothing but that is equals to v of y at that point, of course, yeah, at that point. And vx is nothing but minus of ui. Please remember this thing, vx is nothing but minus of ui. Okay, so this is essentially your CR equation. Okay, so let's look at a proof of this thing. The proof is not very difficult. This is very, very easy. So, see, since the function, the derivative exists, f prime z exists, right? So, f prime z can be written as, so I'm not giving you the exact line by line proof, I will just give you an idea of how the proof works. So, this is nothing but limit h tends to 0, f of z plus h, this you already know, right? Minus f of z by h. Now, you see, if we break this part up, if we break it up, so define h as h1 plus I h2. Yeah, if we define it like this, okay, then that particular term, f prime of z, yeah, see, this exists, this is given. Since it is differentiable at the point z, this particular derivative exists. This is the idea. Yeah. So this is nothing but limit h tends to 0. Now let us break everything up. So it is nothing but u of, see, z is what? Z is nothing but x plus I y, and h is nothing but h1 plus I h2. Yes. Okay. So here f is f, you remember, it is u plus I v. Yeah. So z plus h is x plus h1 plus I y plus h2. Yeah, this is z. Okay, so that will give us f of x plus h1, u of xy, right? And y is y plus h2. Yeah, and this is u plus I v. V part again will depend on x plus y1, x plus h1 and y plus h2. Okay, minus u of xy plus minus I v of xy. by h by h. Okay, I hope this is clear. So essentially what we did is we broke everything up into real and complex part. Now I know that this limit exists. So essentially this is nothing but limit h tends to 0. Let's break up the real and complex part, separate out. X plus h1 minus, comma, y plus h2 minus u of xy by h. Okay, so you can write it like this: plus I times, okay, v of x plus h1 y of h2 y plus h2 minus v of xy by h. So this exists, that is the point, this exists. Clear? See, if this exists, then I can approach h from any particular direction and this particular thing should exist. That is the idea. Clear? Okay, so now what we do is this: see that take the path, okay, h, initially first of all I will take h2 to be 0 and h1 is going towards 0. This is the path we are taking. Now if you take this path, what happens is this: you see it becomes limit h2 goes to 0, okay, u of x plus h1 minus u u of x plus h1 and y, because y plus h2 is 0, so it becomes y, minus u of x comma y by h1. Clear? See, one small mistake, this should be h1. Yeah, h1 goes to 0. So h divided by h is h1 plus I h2 is 0, so basically it is h1. So this is what, now you see this is nothing but limit h1 tends to 0, u of x plus h1 y minus u of xy by h1. See, the whole limit, this particular limit exists. So along any path, the limit should exist, right? So essentially this particular limit exists. And so what exactly is this? This is nothing but ux at the point x comma y. Clear? Now again, limit h1 tends to 0, v of x plus h1, okay, and h2 is 0. So basically y minus v of x comma y by h1, right? So this is nothing but vx at the point x comma y. Okay, right? So what did you get? Therefore, you see both this limit, this exists, because the original limit exists. So along every path it exists. Okay, so essentially these two particular thing exist. So you see what happens is f prime z can be written as ux plus I vx. Yes, this is a formula, actually a very, very important formula. See, f prime z exists. So if the derivative of f exists, that is why along any path, along this path it exists, along this path it exists. So basically this path, this becomes ux, this becomes vx. So f prime z is nothing but ux plus I vx. Also, now let's look at the other part. You see, if you take limit, so essentially you take this path, take h1 is 0 and h2 goes to 0. Then limit h2 goes to 0, u of, so let's look at this particular thing, u of x y plus h2 minus u of xy by h2 plus I v of x y plus h2 minus v of xy by h2 by h2. Clear? And if you write it down, this again, along this path also the limit exists. This we know, right? Along this path the limit exists. This we already know. So if we write it down, what happens here is this. I hope this is correct. Huh? This is nothing but limit h2 tends to 0. U of x, this particular term is nothing but u y of x comma y. Okay, and the last, the next part, this particular thing is plus I times v y of x comma y. Okay, so you see we can break it up into two different paths. Okay, I have missed a I here. I have missed a I here, so I can write it here. Okay, because h is h1 plus I h2. h1 is 0, so I have missed that I. So this is nothing but 1 by I, and there is no I here, that gets cancelled out. This is no I. Okay, no I. Okay, so see, if f prime exists, then along any path it exists. So you see here what happens is, therefore f prime z, you can also write it as 1 by I is nothing but I square by I, which is I. Yeah. So you see, you can write it as I times uy plus vy. Yeah. You can also do that. Absolutely no issues. Both are fine. Okay. Right. So you see, since f is differentiable at z0, at z0. Along every path, the derivative, value is going to be same. Therefore, ux plus I vx should be equals to vy plus I uy. Okay, and therefore, if you take the real and the complex part together, what happens is it gets you ux equals to vy. Okay, and vx equals to minus, oh sorry, there is this is minus, this is minus. Okay, there is a minus. See, I square is minus 1, so I square by I is so if you are doing 1 by I, sorry, so 1 by I, so essentially if you are doing by I, it is minus I, right? Okay. So 1 by I is minus I, so this becomes minus I times vy. So vx is nothing but minus u times y. Clear? Okay, so you see, and this is nothing but your CR equation. This is nothing but CR equation. So essentially what it is saying is, this is a test for a function to be differentiable. If the function is differentiable, ux has to be equals to vy and vx has to be equals to uy. Okay, now let's just look at this particular thing and see that what does this say about our original function. So let's say example, you see fz equals to z square, we already know it is differentiable. Yeah. Okay, so does this satisfy the CR equation? See, fz equals to z square. Yeah. If we want to find out if it satisfies CR equation, what we do is this: we break it up into real and complex part, right? This is what we do. Okay, we write it like this: f of z is z square is x plus I y square. So that is nothing but x square minus y square plus I times 2x comma y. Yeah. So now define u of xy to be x square minus y square and v of xy to be 2xy. So you see, in this case, f of z is u of xy plus I v of xy, right? Now let's just look at whether CR equation is satisfied or not. We know already that this is differentiable, so it should satisfy, right? Let's just check. So what is ux? Ux is, this is a function from R2 to Rc, so we can already do our ordinary partial derivative. So ux is nothing but 2x. Uy, what is uy? It is nothing but minus 2y. Okay. And what is v of x? Vx is nothing but 2y. What is v of y? It is nothing but 2 times x. So you see, ux is nothing but vy. Therefore, ux is nothing but v of y. And what is vx? Vx nothing but minus u of y. And u of y is nothing but minus v of x. Here, so it satisfies. Therefore, it satisfies the CR equation, which it should, right? Satisfies the CR equation. CR equation. Now, you see, it is very, very easy to show something is not differentiable using CR equation also. So, let me give you an example. What we already know, but I have just said it, I did not prove it explicitly, that fz equals to z bar is not differentiable. Yeah. So, let's just say if it is if it is differentiable at the point z naught, it means that CR equation is satisfied. Okay. So, you see, if it is, so what is the contrapositive statement? The contrapositive statement is if CR equation is not satisfied. What does it say? It means that will imply that the f is not differentiable. F is not differentiable at that point. Yeah. So you see, let's take this example. Fz equals to b. Take fz equals to mod z. Okay. Let's just see if CR equation is satisfied or not. Then again, for CR equation, you break it up into R2 to R function. So f of z becomes x square plus y square. Okay. Z is x plus iy. So mod z squared is nothing but x square plus y square. What about the complex part? There is no complex part in this particular case. At to the power half, that particular thing is there. Yeah, to the power half. Okay, so let's just make our life a little bit easier. It makes you z square. Doesn't really matter. You can do to the power half also. Let's just do it with z square. Okay. Okay. So if fz equals to mod z, it is becoming x square plus y square whole power half. But I mean, just a little more calculation. I don't want to do that calculation. I will do it like this. Yeah. But fz equals to mod z is also going to be the exact same thing. Okay. So in this case, what is u of xy? U of xy is nothing but x square plus y square. Okay. And what is v of xy? V of xy is nothing but 0. Yeah. Then you see what is ux? Ux is 2 of x. 2 of x. So if z is not equal to 0, x or y, either one of them is not 0. So if z is not equal to 0, either x or y is not 0. Either x or y or both is not 0. Right? So in this case, you see ux equals to 2y, which is not equals to vy, because vy is always going to be 0. If x is not 0, this part is not satisfied. Also, you see uy is what? Uy is 2y. That is not equals to vx, which is 0, if y is not 0. So you see, either one of them is not 0, right? So basically, one of the equations is not satisfied. For the CR equation to satisfy, both has to be satisfied, right? So therefore, CR equation is not satisfied. Is not satisfied. And what does it mean? Satisfied at z not equals to 0. Yeah, that will imply that the function is not differentiable. Function is not differentiable at z not equals to 0. At z not equals to 0. It is actually differentiable at z equals to 0. That you can of course see, not using CR equation. Yeah, but the thing is, you can just have to put everything in the equation itself and see that whether it satisfies the CR equation or not. Yeah. So with this, I am going to end this video, and in the next video, we are going to relate the idea of CR equation and derivative. So essentially, here we showed that if the function is differentiable, it satisfies the CR equation. In the next lecture, what we are going to see is just satisfying the CR equation. Is that enough to show that the function is differentiable or not? So thank you so much.